All right. Ladies and gentlemen.
Hi.
Hi, aloha, and thank you for coming. I'm Dr. J.D. Armstrong. I'm the Maui Technology Education and Outreach Specialist. And one of the things I get to do is put together these talks, and usually I give the introduction, but today we're going to try something new. I'm going to introduce the person who will give the introduction. Many of you know Stan Truitt. He has a really impressive career. He's started out at 16, wasn't it, making optics at Cave Optics.
That's right.
And he was in the aerospace industry in the late 1950s, went on to weapons like ICBM, then information gathering, black airplanes, worked for Lockheed Martin on the Star Wars project and some other things there. He retired from the military observatories here on Maui, and in fact he was one of the people, if not the lead person, that wrote the specifications for AOS. And now we have brought him into our fold. He works with us around here at IFA, and so, as I would like to point out, he's a master optician. And so I'll turn the time over to him for a good introduction now.
Oh boy.
All right.
Here's some more. Thank you. Welcome everybody. I rarely get an opportunity to that's so pleasant to introduce a person for whom I have the highest regard. He's a good colleague, very learned, and has added greatly to my experience here at the IFA. His title here is visiting scientist, and he moved to Maui after his retirement as professor, and he was the director of the Planetary Plasma and Atmospheric Research Center at the Tohoku University in Sendai, Japan. Got out right about earthquake time, huh?
Yes, yes. So we have
the Sendai province is where it was really. Yeah, and in this, I noticed when I read a little bit more about his personal stuff, is that in 1956, when he was 9 years old, there was a close approach of Mars. He had a 4-centimeter telescope, and he kind of got bitten by the astrobug, I think, looking at that little red dot. Of course, at a 4-centimeter telescope. Did I say 4-inch? I meant 4 centimeters. 4-centimeter telescope. About 2 inches, a little under. All you can see is the little red dot. You can't see anything else, you know. But that was enough. And I had a similar thing. My very first telescope was almost exactly the same size, and I was similarly bitten around the same time. Okay. Then things that he thought and intended at the time was, what worlds exist other than Earth? So that was his internal question. And are there completely different creatures living somewhere? Can I see them? Okay. And he wants to see all over Earth. Well, am I not loud enough?
You're breaking up upstairs, so. There you go. Sorry about that.
I can hear me now. Okay. All right. After that auspicious childhood beginning, in 1970, he finished his physics courses at Tohoku University. And then later on, he just re-upped, and in 72, he was employed as an engineer there as well. And in 1977 through 79, he stayed at SUNY, it was a university in Albany, upstate New York, as a research associate. And then he went, in 1995, he went to the National Institute of Polar Research, and he wintered over in Antarctica at the Showa, okay. My Japanese is a little lacking there. Stationed in Antarctica, wintering in Antarctica. Now that's an adventure, huh? Okay. In 1999, back to the newly established Planetary Plasma and Atmospheric Research Center at Tohoku, where he was the director. Is that correct? Okay, and in 2012, he retired. Get out all exciting work, huh? And moved to Maui for the Planets Project, on which I also am working, and who I'm having a great time collaborating with Shoichi. I've been mispronouncing his first name even. Well, anyhow, with great pleasure and looking forward to his talk, I give you Dr. Okano.
Thank you very much, Stan. Do you hear me? Okay. I'm very happy and I feel honored to have this opportunity to speak to you. Okay. Today, I'm going to talk about, as Stan said, my first experience for planetary observation was when I was 9 years old. And I measured, when I go into the university, I wanted to measure astronomy, but my parents, including my teacher, they all stopped me, because if you measure astronomy, you cannot get job, you cannot eat. So I measured geophysics, and then after that, when I go to the graduate course, I switched to geophysics, and I have been making research in the upper atmosphere for many years, but from year 1999, yes, it was 1999, I started planetary science as I wanted. And after my retirement this year, in March, I moved into Maui, and I lived here almost 6 months. So that's my CV. And I start my talk. This is outline. And I think I have to introduce myself, why I'm staying in Maui. And then spectroscopy. This is the method, the best way to explore planetary world. And I'm talking about this technology, laser heterodyne spectroscopy. This is the best way to explore planetary atmosphere. This has the highest resolution in the world. And I'm talking about the example of our observation, what was done at the summit of Haleakala. That is Enceladus. Enceladus is one of many moons of Saturn. We could detect the emission, light emission from Enceladus, Taurus. And finally, I'm going to talk about a new telescope project called Planets. So, as the Stan has already introduced myself, but my first visit to Haleakala was 88. almost 24 years ago. And at that time, my target of observation was not planets, but I made the observation of stratospheric ozone, this laser heterodyne spectroscopy, and I made that time I made the observation of air glow. I'm going to talk about air glow a little bit later. And as Stan said, I wintered over at the Japanese Showa Station in Antarctica. This was for aurora observation. I had to renovate the equipment in Showa Station for digital recording. And after I returned to my Tohoku University in year 2000, I started planetary observation at the summit. And I came into Maui this June. This is a picture at the time of my first visit here, year 1988. This equipment is for making all sky observation of air glow. And this is zodiacal light battery. And at that time, we had no Fox telescope or AEOS telescope. And this tower is for measurement of microclimate for AEOS telescope at that time. And this picture, this equipment is laser heterodyne spectrometer. And we had a severe storm at the summit. When I showed this picture to my friend, I joked that this was taken in Antarctica. They believe. And year 2000, I started planetary observation, and year 2006, we constructed a small dome, 2.6 meter, and we telescope. This is a kind of amateur telescope, but with these equipment, we made some interesting observations. So I'm going to talk about that. This is our first dome. And in year 2006, we construction of this small dome and 40 centimeter telescope. And we prepared our homemade spectrograph. In the back row, Maui. And there's Karitani-kun, 手を挙げて。Okay, this is an example, example of image data. This is not our data, but to take a picture of, this is Mercury. When you see Mercury in the dawn sky, or this is the direction to the sun, and anti-sunward, the Mercury has very long tail. This number is Mercury more than 1,000 radii. The tail extends. So if your naked eye can detect this, the length of the tail would be more than twice of the moon radius. This is this emission is orange color, sodium color, and we could record the close to the Mercury, how the Mercury atmosphere. The Mercury has believed to have no atmosphere at all, but actually it has very thin atmosphere. That atmosphere is made by interaction from the solar wind and solar ultraviolet radiation onto the Mercury's surface. The sodium atoms are released from the surface ground, and it is because of solar radiation pressure, it is accelerated to the anti-sunward. This is called a spectrogram. Later on, I will talk about spectroscopy much in detail, but this is wavelengths. This is wavelengths, and this is space. This direction is space. So in the space, we have Mercury here. Mercury has reflection of sunlight, so the sunlight is a continuous light, and we have these two lines here. This is sodium D line emissions, D2 line and D1 line, and this straight line is emitted from upper atmosphere, our upper atmosphere. And Mercury is orbiting around the sun, so the Mercury has a relative velocity from the Earth. So the emission from Mercury has a Doppler shift, a little bit difference in the wavelengths. This is the left side line is from Mercury. And if you see in detail this picture, the separation between these two lines gets bigger and bigger as we go away from Mercury. This means the sodium atoms released from Mercury is being accelerated. So this is very interesting data. And also we have been continuing Jupiter observation for many years. The Jupiter is the largest planet in the solar system. And Jupiter has many satellites. There are 4 of them, and the innermost satellite is named Io. And okay, this picture was taken And we can see this volcanic eruption. Okay. Okay. And because of this volcanic eruption, Io has an atmosphere. And the atmosphere is neutral, electrically neutral, but it is ionized by solar radiation, and the component of this atmosphere contains sulfur atoms and sodium atoms. And once it is ionized, it is trapped by very intense magnetic field of Jupiter. Jupiter has magnetic momentum that is 20,000 times stronger compared to our magnetic field. And Jupiter rotates with a period of, okay.
We are having a little trouble with sound, so we apologize to
the upstairs. Can I? Yes.
We're going to try this.
I'm afraid I'm speaking very in good English or not, but if you don't understand, please interrupt me. Okay, and I show you this is a moon. This doesn't work. I'm very sorry. I'm sorry. Oh no. This should work. Okay, then I try this. No, this doesn't work. Okay.
We try so hard.
Yes? Huh? Yes, I have file in my memory stick. Yes, if we have time, okay. Okay, then I suppose it does work. This shows how this is Io, satellite Io, and we are supposed to see the Io is rotating around Jupiter, and then the sulfur ion and neutral sodium, and they have different shape. I wanted to show that, but the sodium nebula, of Jupiter. So this volcanic eruption contains sodium atoms, and then it is spread out from Jupiter to very huge space. This one is 2007, May 22nd, May 29, and June 12. So within less than 1 month, the nebula, shape of nebula, changed very much. So the extent of this extension is almost, this is 100 Jupiter radius. So Jupiter has 70,000 kilometer radius. So you can understand how this extension is large. If we can see this nebula by naked eye in the sky, the extension would be few of lunar radius. So what we are going to do is we observe this variability change of sodium nebula from the summit of Haleakala, and then my colleague is making observation to see the volcanic activity. And then next, spectroscopy. As you know, the light is a kind of wave. What kind of wave? It is a wave of electromagnetic field. Electric field is going stronger and weaker, then repeating it, and traveling with speed of light. So the wavelengths, we can define wavelengths. So from short wavelengths to long wavelengths, the only portion of the electromagnetic wave, we can see that this is visible range. This is ultraviolet. And the longer wavelength is called radio wave. In this part, that we have X-ray. The size of wavelength, our visible light is somewhat smaller than factor D. And the size of atom is equal to X-rays. And what is the source? Our body is emitting ultraviolet infrared radiation. The visual light is coming from light bulb. And in the space, the cosmic source is the planets. Planets radiates infrared emission. And the sun is radiating visible light, as you know. And I have to talk about spectroscopy. We have a hot light source, like bulb, and then we put slit is rectangular shaped. If we have a slit on in a board or something, and behind it if we put the prism, the light source has a continuous light, so we can see the light like this. And we gas with sufficiently high temperature or something. This is energized, and then the light has discrete light emission, not continuous. And this is a fingerprint, something like a fingerprint of this gas. If this is, I think this
Looks like sodium again.
on the contrary, this gas, put light source like this, the high temperature light source. Then we have this kind of absorption spectrum. The same thing, sodium, if we put sodium gas here. In this case, we have emission spectrum, and in this case, we have, at the same wavelengths, we have absorption. This is a basic of. And so if the resolution, spectral resolution is low, we will have this kind of spectrum. The spectral resolution is determined by the width of slit. And if we have very narrow slit, then we will see this more sharper spectrum like this. And if we observe planetary atmosphere, this is Venus. All of them have absorption microns. This is because of carbon dioxide. All of these planets has carbon dioxide. We can know what component of atmosphere is that on that planet. The Venus has H2SO4. It is sulfuric acid. And in our atmosphere, we have ozone and water vapor. The existence of ozone in our atmosphere has a very important meaning. Because of ozone, we can live. The ozone protects us against very harmful solar. Next, I'm going to talk about laser heterodyne spectroscopy. This technique is now being made at our university and in Germany and in NASA Goddard Space Flight Center. This has this technique has a very high sensitivity and ultra high precision. The first of this we observe the planets with telescope, and light from planet is mixed with laser emission. I'm sorry to put these equations, but the idea is, as I said, the light is wave, so it has frequency or wavelengths. When these two frequencies are very close, then the beat frequency will be produced. And this principle is similar to radio. In radio technology, I think you have heard about super heterodyne technology. This is the same principle. So the infrared light has some frequency of about 10 to the 13 hertz. But using this laser local oscillator, we can convert the frequency down to radio frequency. So we can use radio technology to get spectrum in infrared. It is very useful. Almost this equipment, to upper one is observe the spectrum, and this is made first in the world. At that time, the laser power was insufficient for planetary observation. We need a large telescope, large aperture telescope, and powerful laser. In recent years, this new equipment, and they succeeded to make observation of ozone again. I'm going to use this technology for planetary observation here in Maui. And I talk about a good example of our observation at the summit. This is Enceladus. This is a Saturn system. So many. This has a diameter of about 500 kilometers. Very tiny, very small moons. Enceladus, and this is not visible, but with a powerful telescope or from spacecraft, it can be observed. And this is Enceladus. In the south pole of Enceladus, we can see something is going out. And this picture was taken by Cassini spacecraft. Detection of this plume was in the year 2004, I think. And this plume was identified as water ice particles. So the water ice dissociated by ultraviolet radiation from the sun. And then it will be ionized by ultraviolet radiation or charge exchange something, and then it will become ions, plasma, and then it sputters inside the surface, and some of them will be lost, transportation, something. I thought if there is oxygen atom, it will radiate light emission. So I tried to detect it. And this is a picture of Cassini spacecraft. And in this case, the sun is behind and very clear. And this is an expected mechanism of light emission. Electron impact, or the OH molecule is dissociated by ultraviolet, or impact of water molecule with electron, or water vapor molecule dissociation. We have excited oxygen atom, and then excited oxygen atom will emit light at a wavelength of 100 nanometers. This is red emission. And with 50 centimeter scope and the spectrograph, we put slit here. And then we could detect the emission from us. Yes. So this is too bright. So inside the torus. And this is the spectrum. This is and in we could get the emission as expected. This shows the north-south distribution. And this is low spectrograph. And this is space. So this is the emission from air glow. Our atmosphere is emitting. So I'm going to show you the interesting movie here. Last the big broadcast company in Japan the crew of NHK came to Maui to make this film. So I want to show you this.
Can we kill the lights?
Oh,
Good.
it doesn't work. Huh? It works? Yes. It did work. Yes, okay. Okay. I'm sorry. This is the first astronaut, John Glenn, year 1962. He lost attitude control. He detected mission. This is all from Space Shuttle. This is the way to summit. Very, yeah. You see the change of color. This. So this, I should stop now. This is called air glow. Okay, now back to now, as you see, the whole Earth, whole globe is surrounded by this air glow emission. I think the summit of Haleakala is the only place we can see the air glow by naked eye. I tried to see the air glow with my eye at many places, but the summit is the only place. If we see the air emission is this is ground. Okay. This is ground. Air is being emitted at high altitude, more than 250 kilometers high, and it has some emission layer. And if we see overhead to the Venus, the emission is very weak. But if we see in slant direction, the length in the emitting layer increases. So the amount of light will increase. So if we see around the horizon, we can see the air glow with naked eye. So,
are you saying air glow?
Yes, air glow. So the next thing I have to talk about is Planets Telescope project. This is a new telescope project that is proposed to be constructed at Haleakala for planetary observation. And the reason is in observations of faint emissions close to a bright planetary disk, we always suffer from contamination of scattered bright background continuum. So we need a telescope with minimum scattered light. To minimize the scattered light, we need a very smooth surface of mirror. And our current telescope is a Schmidt-Cassegrain telescope, so it has a Schmidt collection plate that is made of glass, so it makes impossible to use it for infrared observation. That is very useful to study planetary atmospheres. So we need a completely reflective telescope. And long-term continued monitoring with a dedicated telescope is required for observation of planetary plasma and atmosphere. So this is the reason why we need a dedicated telescope.
How many meters do you hope?
I want to have more than 1.5 meter. And the planets is called the abbreviation for polarized light from atmospheres of nearby sphere system. This project is an international project with partners from IFA. The principal investigator, the leader is Jeff Kuhn, and Tohoku University, my university, and Universidad Nacional Astronomía Mexico, Mexican University, and private organization, and Kiepenheuer Institute for Solar Physics. This is in Germany, and Finnish University. We had a meeting in Mexico 2 years ago. This is a group photo at the time. And Stan is here, and Jeff is here, and Isabel is here, and Masato is here. So these are Mexican people, and Svetlana is from this institute. She shares my office, but she is now in Germany. And our proposed telescope is 1.8 meter diameter. And the advantage of this telescope is this is off-axis optics. The conventional telescope has secondary mirror inside the incoming beam. And as I said, the light is a wave, so if we put something in the wave, just like if we put a rod in a river flow, it will disturb the flow. The similar thing happens if we put the secondary mirror inside the incoming beam. So we are going to put the focus outside of the incoming beam. This is called off-axis. And we want to have this telescope at the summit of Haleakala. And this is a conceptual design of our telescope. And in Japan, we made the glass. I took this picture when the glass was coming out. And as you know, we had a big earthquake in my town, in Sendai, last year. At that time, this glass blank was just finished. So when I come down from my office in university, my first concern was the glass bank is safe or not. Yeah. But finally it was safe anyway. And this year the glass bank was shaped in Rochester, New York. So the was finished. Move on to polishing process. And for polish, the
Make these things in Arizona too, as you know.
hydro. This has no pressure on the surface. If we have a pressure, it will deform the glass shape. Mirrors. And this is conceptual design of Planck's telescope and the building structure and the dome. So we aerial view of the summit, and this is Fox telescope. Opposite to Fox telescope, we have this old building, and this is officially this is called Neutron Monitoring Observatory, and to replace this with a new building. And when this new telescope, Planck's telescope, is completed, a laser heterodyne spectrometer, as I told you, which is now ready in Japan. This will be coupled to telescope to detect life-related molecules in atmosphere on other planets and even on exoplanets. So my first desire when I was a child, as Stan said, now it's for instance, activity means but we cannot travel to exoplanets. So only exoplanets means extraterrestrial planet, the outside of our solar system. The exoplanets, the many exoplanets, more than 600, have been detected already. So some of them has Earth-sized diameter, and if exoplanets is in habitable zone, habitable means very adequate distance from the mother star, there is a possibility of life. So I think, yes, please. I wish to finish this project as soon as possible. That is what I can say now. We are going to use this for science. And before I die, I can detect some sign of or trace of life on other planet. Thank you. Thank you.
Your lifetime.
Yes, my lifetime.
What wavelengths of light does this operate on?
What wavelengths you mean for this telescope? The instrument for this telescope will be visible spectrometer, and infrared. Infrared means something 1 micron to 10 micron. Yes?
Besides methane,
Yes.
what other light-related molecules do you look for?
In exoplanets, I would say the water vapor, water molecule is maybe important, very important.
What about ozone?
Yeah, if we can detect ozone, it means that planet has oxygen atmosphere. It is very important. Yes. Yes, please.
What detector are you using for your nonlinear mixer?
Non-linear mixer, it is, I'm using mercury cadmium telluride MCT detector.
And what's the rough RF radio frequency that you're using for that?
The frequency response is, our present detector has a response up to 1 gigahertz. It is only available in the United States.
And you can go down to what's the narrow bandwidth you go in gigahertz? A tenth of a gigahertz?
Yes, that is a good question. The narrower the bandwidth, the spectrum will be better. So we have a radio frequency spectrometer, and it has a resolution of few tenths kilohertz.
Okay.
Mm.
Very, very narrow.
Yes.
Does Venus have a tail? And does the Earth's
Ah.
ever go through the tails of
Okay,
planets?
it is also a good question. The Venus has no sodium. As far as I know, we didn't detect sodium on Venus, but Venus has very thick atmosphere. The atmospheric pressure on Venus is almost 90 atmospheric pressure, 90 times on Earth. So such thick atmosphere will be ultimately, finally, it will be dissociated and it will escape into the space. So detection of such escape from planet will be very important. Yes.
Isn't it expected that the sulfuric acid in Venus's atmosphere would have a high probability of combining with sodium and make sodium salt?
The origin of sodium in the atmosphere, in planetary atmosphere, is in many years ago, when I was a college student. It was believed that the sodium in our atmosphere is coming from space by the evaporation of meteorite or something in the high upper atmosphere, or coming from ocean. But finally, it is concluded that the sodium is coming from meteorite.
So continuous.
Yes, yes.
I have another question
Yes.
about the air glow.
Yes.
And the color change in the air glow.
Yes.
That was fascinating. I never
Yeah.
saw it so strongly. Is the
Okay.
difference the excitation?
Yes, yes.
Or the material?
Yes, yes. The light emitting species is oxygen. The both for green and red. It is from oxygen atom. Oxygen, we have oxygen molecule in this atmosphere. 20% of our atmosphere is oxygen molecule. But in upper atmosphere, it is dissociated by solar ultraviolet radiation. It is dissociated into atoms. And then the red emission from air glow is from recombination of O2 plus ions with electron. The O2 plus ion is produced by O plus ion collided with O2. And so it has something to do with electron density. So in evening time, evening twilight, right after sunset, the upper atmosphere, the ionosphere has a very high density, high electron density. So the red emission is very strong in twilight, evening twilight. But in midnight, the red emission is getting weak and weak, and then green emission. Green emission is, has a different mechanism, different production mechanism.
Thank you.
Okay? Okay. Thank you so much. Thank you so much.